Hey everyone, welcome to this explainer. As a civil engineer consulting out on construction sites every day, I see a lot of misconceptions in the field, and I really want to kick things off today by positioning plaster correctly. Way too often, it's just viewed as a visual finish, something to make a brick wall look pretty before the painters show up. But that's missing the point entirely. Plaster is a building's vital armor against the elements. It literally dictates the structural legacy and longevity of everything beneath it. If we don't get the engineering behind the plaster right, the masonry fails, moisture intrudes, and the whole building suffers. So today, we're going to master the actual technical science of wall plastering.
Here's a quick look at our agenda. First line of defense, internal versus external mixes, demystifying the volume factor, step-by-step material estimation, and finally, pro tips for perfect plastering. Let's dive right in.
Section 1. First line of defense.
Okay, so plastering is the critical damp-proof barrier that ultimately dictates your structure's lifespan. Just look at this exposed multi-story exterior. External plastering is literally your masonry's shield against harsh weathering. We're talking driving rain, severe humidity, and wide temperature swings. Without this dense protective layer, water would just easily soak into that porous brickwork, leading to dampness, structural decay, and basically an absolute nightmare for whoever's living there. But beyond acting as this heavy-duty armor, a properly leveled plaster surface also gives you an ideal, really economical base for decorative treatments like painting. It covers up any, let's say, defective artistry in the masonry work underneath, ensuring the whole thing is both impenetrable and looks great.
Section 2. Internal versus external mixes.
Let's explore the why behind our mortar ratios, because the surrounding environment absolutely dictates our structural reasoning here. When you're specifying a plaster mix, you really can't use a one-size-fits-all approach. Think about it. An external wall is fully exposed to the elements, right? So it requires a much richer mix, specifically a 1:4 ratio of cement to sand. That higher cement content gives you superior density, durability, and the essential weather protection you need to stop moisture dead in its tracks. Now compare that to the controlled environment of an internal wall. Inside, the wall isn't fighting off rain or extreme thermal shock. It really just needs to serve as a smooth base for interior paint. Because of that, we can safely use a standard economy mix of 1:5 or even 1:6. Using a 1:4 mix inside isn't just overkill, it's a massive waste of expensive cement. But conversely, using a 1:6 mix outside, complete recipe for catastrophic moisture failure.
Section 3. Demystifying the volume factor. Now this right here is where site estimations usually go completely off the rails. Take a look at this wet mortar mixture. Whenever we calculate the volume of a plastered area, say multiplying a wall's area by the thickness of the plaster, we're initially getting a wet volume. That's the space the mortar takes up when it's mixed with water and ready to be applied. But here's the catch. You can't exactly call up your supplier and order wet materials. To buy what you need, you have to calculate the dry volume. When water hits a dry mixture, the particles reorganize themselves. They slide together, filling the pores and voids, which significantly shrinks the overall volume of the mix.
So that brings us to the magic number, the crucial conversion factor, 1.30. And honestly, sometimes it's pushed up to 1.35 depending on your site conditions. To get the true dry volume of materials you actually need to order, you must multiply your wet volume by a factor of 1.30 to 1.35. If you skip this step, you're going to run out of materials about 2/3 of the way through the job.
Let's break down the actual physics of exactly where this 30% allowance comes from. First up, sand void compressibility. It's kind of wild to think about, but dry sand contains so much air that 20% of its volume literally vanishes the second it gets wet. Those voids just collapse. So right off the bat, your sand shrinks by 20%. What about the cement? Well, cement particles are so incredibly microscopic that their void compressibility is pretty much negligible for this math. So we've got our 20% shrinkage from the sand. Then we have to account for the reality of a messy construction site. Mortar drops off the trowel, gets stuck in the mixer, or just gets left on the board. We factor in 5 to 10% extra for this inevitable labor and handling waste. Add that 20% shrinkage to the 10% waste, and boom, your dry volume has to be 30% to 35% greater than your wet volume.
Section 4. Step-by-step material estimation.
Okay, let's step into the classroom for just a second. I want every site engineer to basically memorize this exact mathematical process. Step 1. Calculate your wet volume. Just multiply your total wall area by your desired plaster thickness. Step 2. Apply your dry conversion factor. Multiply that wet volume by 1.30 or 1.35 to find your true dry volume. Step 3. Take that dry volume and divide it by the total ratio of your mix. That will isolate the exact cubic meters of cement and sand you need to order. Let's see that math in action, shall we? Picture a standard 100 square meter exterior wall with a 12 millimeter plaster thickness. First, our wet volume. 100 times 0.012 gives us 1.2 cubic meters. But remember the shrink. For the dry volume, we multiply that 1.2 by our 1.35 factor, landing us at 1.62 cubic meters. So how much cement is that? Well, in a rich 1-to-4 mix, you've got 5 parts total. For the cement volume, we take 1 divided by 5, multiplied by that 1.62 dry volume, which gives us 0.324 cubic meters. Since one standard bag of cement is roughly 0.035 cubic meters, how many bags do we order? Divide 0.324 by 0.035, and we get 9.25 bags. Let's just round that up to 10 bags to be safe. For the sand volume, just take 4 divided by 5, multiplied by our 1.62 dry volume, resulting in 1.296 cubic meters of sand. Bam! Just like that, you know exactly what to order. Zero guessing.
And finally, Section 5, Pro Tips for Perfect Plastering.
So, perfect math means absolutely nothing if your field execution is sloppy. You cannot just slap plaster onto a flat, dusty wall and hope for the best. You have to rake the masonry joints to a depth of about 12 millimeters, while the brick mortar is still green. This provides a crucial mechanical key, a physical grip for the plaster to actually lock into. Next, establish your dots and screeds. These little 15 by 15 centimeter patches of plaster act as your physical depth gauges across the entire wall. You set these dots horizontally and vertically, checking them with a plumb bob to guarantee absolutely perfect vertical alignment. Once your surface is fully prepped, there are some pretty uncompromising rules you have to follow. First, sand quality. Your sand must be clean and well graded. Clay, silt, and dust strictly need to be below 5%. Anything higher is going to kill your cement bond. Second, time management. The second you add water to that mix, the hydration clock starts ticking. You have to consume that mixed mortar within 30 to 45 minutes. If it starts drying out and a laborer tries to just add more water to remix it, reject it immediately. It's permanently lost its strength. Third, hydration. Keep your prepared brick substrate wet for at least 6 hours prior to plastering. If the brick is dry, it will violently suck the moisture right out of your fresh plaster, causing it to fail. And lastly, curing. You've got to protect the fresh plaster from fast drying by the sun or wind, and cure it with water once it hardens. If it dries too quickly, you'll be dealing with plastic shrinkage cracks across your entire facade. Check out how tightly this finishing coat is being applied. You aren't just painting it on, you really have to force it into the surface depressions with a lot of pressure using a steel trowel. That's how you get a permanent, flawless bond. And pro tip, always try to work from the top of the wall down to the bottom in one continuous operation to eliminate those ugly joining marks. So I want to leave all the contractors and site engineers out there with this slightly provocative question. Are your current site practices truly optimizing both your material costs and the long-term structural integrity of your buildings? Are you actually taking the time to calculate that 30% wastage factor properly? Are you strictly enforcing that 1-to-4 mix for external defenses? Are your masons raking joints and wetting the substrate for 6 hours before they even begin? Because if you're cutting corners on these vital, hidden steps, your plaster isn't armor at all. It's just a liability waiting to crack. Implement these exact engineering protocols, and you'll build structures that truly stand the test of time. Thank you so much for joining me on this explainer, and I'll catch you in the next one.